Welcome. Moin, as we say in Hamburg. Hope you had a great conference so far. We'll take the next 35 minutes to talk about challenges of running data stores in containers. That's me, I'm Johannes. I'm working for a company called Neo4j. So we're doing a graph database. So when you have highly connected data and you want to make sense out of your data, you might want to look at a graph data store. So it's commonly used for fraud detection or like recommendations, or the Panama Papers was analyzed using a graph database. But it's not the topic of that talk today. Today we want to talk about databases in containers. And I'm working in a team implementing database as a service offering. It's called neo4j.com/cloud. And I want to share our experiences with you and the things we made, and want to talk about that today. Before I joined Neo4j, I worked for a company called Mesosphere. You maybe heard of them. They're doing DCS and also be the main contributor to Apache Mesos. So excuse me if I put in a lot of knowledge about Mesos in this presentation as well, beside Kubernetes, for sure. OK, so let's start with a quick poll. Who's doing dev here? All right, over the half. Who's doing ops? All right, also quite a lot. Who's running a database? Everyone loves databases, right? Great. So who's running database in a container? In production? Great, still a couple of hands up. So if you have time after the talk, let's chat and share experience. I would be super interested in your experience running a data store in containers. OK, but let's start. Let's start about data stores without containers. So I want to introduce the term beefy server. So when I did project business for German companies, it was typically this behavior. So we needed to set up a new project. So we went to a sysop and said, hey, let's get us a server. And he went out and bought the most expensive hardware with the most expensive support plan to make really sure that the database will never crash. And this is a beefy server now. OK, so the sysop went out, bought a beefy server, installed a database. I'm sorry that I'm using our database logo. Feel free to imagine that this is an Oracle logo or something else. And then he did the configuration, added the secrets, and all that kind of stuff you need to make to work a database work. All right. Then he bought a second beefy server to install an application server. It's a Tomcat in this example. But don't forget backups. So we was mostly in the confidence that our beefy server will never go down, so we went with nightly backups. Seemed a good idea. But what happens if our server crashes somewhere around noon? So we lost half a day of information. So it's pretty bad. But let's assume our backups were working and someone tested the recovery. Our sysop needed to go out, buy a new beefy server, install a database, and well, all that other stuff. I think you get the point. So we want to get rid of manual interaction when we're running things in production. And this is true for all systems. It's not necessarily related only to data stores. Most of you had this or that. So I imagine a funny discussion I had like 5 years ago. We went to a service provider, like a hosting company, who's doing managed data stores for us. And he said, well, we're multi-data store compatible. You can choose whatever data store you want, as long as Oracle is 7, 8, or 9. So it's 5 years ago. Actually, it's pretty sad, but anyways. But maybe I want to use a different database. Maybe I don't want to implement a key value mapper in an Oracle database. And it's great. So it's a great time today. So if you want to go with connected data, maybe you want to check a graph store. If you have relational database, maybe you want to check a SQL database, or Elasticsearch, or Redis, or Cassandra, or whatever else. So probably my marketing team will kill me when they see that slide. But please, choose the data store that fits your data and fits your needs, because you have the freedom to choose the data store today that really fits your use case. So when we now have the choice, and we maybe have a setup where we want to run a graph store, obviously, a SQL store, and maybe an Elasticsearch together, what is the solution? Sure, let's buy more beefy servers to run all that stuff. But when we're thinking about that we will have a cluster for each of those data stores, this will cost us $1 gazillion if we're going to Amazon. But did you heard about containers? Obviously, we're at Container Days. Everyone heard of containers? So let's look at our pictures. It's easy as that, right? Docker run Neo4j, and we're done? Probably not. Because we need to think about more than just running our containers. And that is a tweet, and it's 2.5 years old. And a lot of people know that. So it's a learning curve between containers in dev and prod. And I don't think you can read all of that, but like you see the difference. So when you're putting containers in production, you need to think about security, discovery, networking, configuration, and also orchestration. And the great things, we will talk about like the things that were most rememberable, that we remembered the most when we did our cloud project. But you would argue, well, we solved all their problems for microservices, and that's true. So we have a cluster of beefy servers. When one of our microservices crashes, well, I don't care. I don't have state. I just restart it somewhere else. Where is it? Here we go. And we can just keep going. So our stack will serve user requests and will have a downtime for that. So you could ask, so what's so special about a database? Like, can't we do the same there? But yeah, we do have data. And the last thing you want to have is losing data when you're operating a data store in containers, or like when you're operating a data store. You don't want to lose data. So let's see about what happens to our data. So this little floppy disk is our data. And if the container crashes, while the data is in the container, snap, we lost data. That's not good. We don't want to lose data. So we're going to mount our data to the host, so that if our container crashes, the data is still there, and we can restart a new container with our database connected to the data, and we're still good to go. So, rock and roll, we saved our data. But let's have a look at that. Our entire host is burning. So snap, we lost our data again. Okay, it's enough. Get me the remote storage. I don't want to handle that on my own. And it's a good idea. So no matter what, your container is burning, your storage is safe, your entire host is burning, your storage is safe. So your end user will receive a downtime because your database is not operating. So you have a negative impact on the customer, but your data is still there, you don't compromise your data, and you can keep operating afterwards, after you recovered. I like that picture. Anyways. But did someone set performance? So connecting to a remote storage is per definition slower than connecting to an SSD screw to your box. So we can think about clusters. So Neo4j implements a raft protocol. It don't necessarily important what it is. It's important that as long as you have the majority of nodes up and running, your database is still able to serve write requests. So in that case, we do have 3 containers. Each one has the addition of mounting the volume to the disk. And if one container is burning, it's no problem. We just restart the container on the same node, mount to the disk, and we don't even have cluster data replication. So we can just reuse the data. And the benefit of using clusters is your end user will not receive downtime. So the end user don't recognize that you had a failure at all. So great, we still saved our data. And the same is true if the entire host is burning. So as I said, as long as we have the majority of nodes up and running, our application, our database is still able to serve write requests. That's good. Okay, so then the sysop can go out, buy a new machine, and connect it to the cluster. Then we need a full cluster replication because we have a fresh set of data. And then we're back to normal operations. Okay, good. To wrap that up, I would not recommend to you writing anything important inside the container only. Please mount it somewhere else. if you're in Kubernetes or Mesos world, I would not recommend you to depend on the host volumes and host path volumes, because host path volumes always make assumptions about the host, and this is probably what you don't want to have when you're in a Kubernetes environment. There's a new thing in Kubernetes called local persistent volumes, and it's in Mesos for quite some time as well. And this is basically a label on a local disk. And so Kubernetes or Mesos can try to reschedule something on that disk if it sees the disk again. But you can configure, if you don't see that local persistent volume again in like 10 minutes or something, then Mesos, for example, can reschedule it somewhere else. And if you're in Kubernetes world, you could write a controller who's doing the same thing. Remote storage, from my experience, is always a little bit slower to dramatically slower than the SSD screwed to your box. But on the other hand, it's super simple. So the cloud offering from Amazon, Google, Microsoft is super huge. You can choose different approaches of remote storage. You can choose block storage. You could choose network-attached storage. So there are different databases reacting different to these different kind of storage. So if you want to do that, do yourself a favor and test it. Make a tiny POC, measure it if you are okay with the delay, and if it works for you, fine. Go with remote storage for your database. Or maybe you want to check out one of these sophisticated storage providers like Ceph or Portworx. Or this morning at this conference was a talk by StorageOS, also comparing remote storages. Maybe you want to check out one of these. But the answer is, there is no silver bullet for you. So you need to test what you're doing, you need to measure what you're doing, and also, you need to compare what you're doing. Because every system is different, every stack is different, every technology is different, so you need to really test what you're doing, so no silver bullet. I'm so sorry for you. All right, did someone said multiplexing, like starting more than one container on a box? Cool. Because now we're getting into the fun part. When you really want to leverage the utilization benefit of containers, like starting more than one thing on a box, you maybe should be aware of party people, like other containers adding some noise to your node. We will see how to minimize that impact, but you could have some noise from other containers on your host. Yeah, that's annoying, I know. Okay. But if you have a cluster, you also have network connections between them. And network is also really, really important for databases. So be aware of network party people. The thing is, when you go to Amazon or Google or whatever, and you buy the instances with the high, with a really, really good internet connection, because you have an application and have high network traffic throughput, be aware that everyone who has an application with a high network traffic is going to buy these instances. And you might see that you have a negative impact on the application because everyone is using that network heavily. So I'm not saying that you for sure will see that. I'm saying if you're going to buy instances on Amazon, test if you have a negative impact on network because of noisy neighbors. Okay, yeah, that's correct. Okay, but now I want to have a closer look on CPU isolation and on network, because I was really experienced with operating things on bare metal, operating a database on bare metal, and I think you also are pretty confident in tweaking the hell out of a beefy server to make your database most performant. But you may be not so experienced in running data stores in containers on beefy servers, or running data stores beside other workloads on your containers in a beefy server. But a high utilization saves a lot of money. So if your stack had before 4 beefy servers, and you're able, through multiplexing, to reduce the amount of servers to 2, like you cut your operational cost by 2. So this is pretty amazing. Like, every manager will love you for that. But we need to think about requirements before we're doing this. So we should make sensible assumption about resource requirements. So in the past, when I went to a sysop and said, well, get me a beefy server, he asked how many gigabytes of memory I wanted to have and how many CPUs. And I said, well, I'm operating a database. I need at least 16 CPUs and 30 gigabytes of memory. Maybe this assumption is still true when running in containers, but you can start with lower resource requirements, and when you see that you reach the limit, it's pretty easy to increase your resource limitations to get to bigger requirements. And to achieve a good isolation and limitation of your CPU usage, there are different approaches. So if you're in Kubernetes world, you have this request versus limit configuration. So basically, when you configure a pod in Kubernetes to say, hey, this pod should have at least one CPU, but it is allowed to consume up to 2 CPUs. This is request versus limit. So you get at least one CPU, but you're allowed to consume up to 2 for burst load, for importing data, for running intensive query or whatever. If you're in Mesos world, you have like different approaches. You have CFS, which is completely fair share. So when you say you want to have one CPU, you get exactly one CPU. Or you can have CPU shares. And CPU shares is basically you configure roughly a percentage. So if you say, I want to have one CPU, your container will get at least one CPU. But if the host is idling, and let's say it has 3 more CPUs, this one container is allowed to use all the CPUs in the box. And if you're getting more containers into the host, then Mesos would take care to shrink your CPU time to the one CPU, the time one CPU would offer. But also there's a feature to oversubscribe resources in Mesos. So there are different approaches, but basically what you want to achieve is reduce noisy neighbors, reduce CPU utilization, and make it clear how many resources you can use. And what we saw is that you should think about acceptable neighbors for your database. So it's probably okay to co-locate a data store with another data store because the workload is quite similar. And maybe you want to run like serve static contents or a web server, a Tomcat or whatever. But maybe you want to think twice if you co-locate a machine learning task beside your database, because that thing might produce a lot of noise. So there were some technologies producing a lot of noise. I'm not saying that it will produce always noise to you, but it could be. So you want to think about that. Okay, but how would I connect to my neighbors? So host ports are pretty rare. If we go back to the picture where we had 2 databases, they usually want to use the same default port for the data store. And then they can't both have the default port. Like if you're in SQL world, you can't both have the SQL port and then MySQL port. Okay, so you could use bridge networks or overlay networks. And the funny story behind Neo4j is Neo4j had an issue with bridge networks. So it was not really able to play nicely with bridge networks because Neo4j implemented a binary protocol to connect to the clients. And this was not really well functioning behind a bridge network. So we fixed that, but in the meantime, we shifted to a different approach. So overlay networks. Overlay networks are great. So overlay networks, every container get an own IP, and you have every port exposed, so every data store can have the default ports, but you also might experience a performance degradation, because to spin up the overlay network, you need resources. If you think about weave networks, you start new processes, and this will take time to route the packages. Again, I'm not saying you will receive a degradation guaranteed, but you might want to measure it if you're using these fancy stuff, if you see degradation. And the same is true for inbuilt stuff. So in DCS are also technology involved to do overlay networks, and they also produce a short delay to do that. So they are optimized for that, but you might see some issues. Or, if you don't want to do that, you could deal with random host ports. The funny story behind Neo4j is Neo4j needed to advertise the port to the other cluster members. So it needed the port up front in a static file, which it was supposed to export. But this didn't play nicely with random host ports. So we needed to tweak around with a shell script to get that really working. So we get rid of that and replace it with a proper solution, but maybe you're working with a similar technology and also need to fiddle around to make it work. But how can I connect to my data store then? Though service discovery in the beefy server world was probably easy, because I had my default Neo4j port, which was 7687, so I could configure that to point to the IP and the port. So now we're running in containers, and maybe the port changed. So I don't know if everyone sees it, but the port changed to a random one. It's 9123. So we can't reuse the configuration anymore. And this is true for everything, like not only for data stores, this is also true for microservices and whatever. So you basically have different options to connect to your data store. If you're in Kubernetes or a Mesos, you will get an DNS serve record, and DNS serve records are about to resolve the IP as well as the port for a service. Or you could use overlay networks and IP per container. And if you're in Kubernetes land or Mesos land, you can combine those and have like VIPs or overlay networks or headless services. And what you get is IP per container, like with your default port, and the resolving of a proper DNS A record pointing to all the containers behind a service, for example. And this is pretty handy because everyone understands DNS A records, and you don't need to change your code in comparison to DNS serve records, for example. So DNS serve records, you usually need to change your client configuration, but if you have a proper A record, most clients work out of the box. Or you could use like great third-party tools like Consul for service discovery. So basically, all the producers register there and push their exposed IP and port, and the consumers would query that console and ask me, hey, give me the IP and port for my database. But the thing is, with an external tool, you also need to change your client code. So you need to choose one of those if you want to find your database later on. Okay. All right, so we talked about CPU, we talked about networking, so talk about data again, about backups. So imagine we do have a data set, data 1, we do a backup here, and then we have a really, really important query for us. We create an invoice with the amount of $1 million. And to make sure that our important queries is persisted, we want to use a backup again. So we schedule a backup, but what happens if our data store crashes before the backup happens? So yet again, we lost our data. But no worries, we do have a cluster. So that's the great thing we learned, is if we use clusters, we are fault tolerant against node failures. And if we use frequent backups, or like if we use backups, and then store the backups to some persistent storage, we are pretty good to go and very confident that we don't lose data, because the cluster prevents us from immediate data loss and also gives us some benefits and performance. But the frequent backups will secure us in the long term if the entire data center will explode or something else. Okay, so are we done yet? No, we have 10 more minutes. So if you saw a talk from me before, you probably know the next slides, but you can't stress it enough. When you talk about containers in production, we need to talk about scheduling, like where to place a container and when to place a container. We talk about resource management, like we talked about resource management. So we need to restrict the consumption of resources in our containers. And we need to talk about service management. So we need to make sure that these services find each other and that we got service discovery that they travel to roughly the same direction. And when we're talking about scheduling, resource management, and service management, we're talking about container orchestration. And like this is super in this venue, right? There are containers all over the place, and I really like containers, but actually we're talking about that. So when we're talking about scheduling, we're talking about where to place containers. So is it okay to start all 3 containers of my cluster in the same host? Probably not, because when this host is exploding, we'll lose our data again, and we hopefully rely on our backups. And we need to talk about replication and scaling and upgrades. So a rolling upgrade for a database is pretty much straightforward from a regular rolling upgrade. Besides the fact that you might want to wait a little bit longer, so you need more sanity checks, because you need to wait for the new nodes to catch up with the existing nodes. So you need to wait until the data is replicated before you can kill the old ones. We pretty much talked about all the resource management stuff and most of the service management stuff. So to service management, you might want to introduce namespaces to separate different parts of your application against each other so that they can't see them. And maybe you have dependencies. So maybe you want to start your Tomcat when your database is ready. So something like that. So we need to think about all that stuff and way more. But I think everyone at this conference is discussing these stuff. So my advice to you, please don't try to implement a container orchestrator on your own. I tried to do that in 2013, and it was a horrible idea. So we were a startup, and we thought, well, we're putting everything in containers, and we only have a short REST API to start and stop containers and shell out to Docker. Failed miserably, but we learned that we can reuse existing container operators. So most of you might be familiar with Kubernetes. So I work for a company behind DCS, so I know this very well. Mesos has a really long history also in operating huge stateful workloads. And I know that there's a couple of other options out there. So you could choose Docker Swarm, for example, or Ranger, or whatever. I just don't know them, and I just don't have production experience with them. So we will focus in the last great 7 minutes about what we did to implement neo4j.com/cloud and what we did to not lose data of our customers. So every database in Neo4j Cloud runs on Kubernetes because we think Kubernetes is a great platform to run databases. And the great thing is we do have managed Kubernetes. So we can go to Amazon, we can go to Google, we can go to Microsoft and buy managed Kubernetes. Because we're pretty good in operating databases, but we're not really good, or we're not as good as we are operating databases. So we're not so good in operating Kubernetes itself. But we can buy in the knowledge from those big vendors. And seriously, who else is experienced with run Kubernetes than Google? Though we buy in this experience. And we wrote a Kubernetes operator. So a Kubernetes operator is basically a process querying the Kubernetes API and comparing the target state in etcd to the current running state. And the target state is something like this. So you can talk to Kubernetes, and you can extend the Kubernetes API with your own types. And we did the Neo4j cluster type. And we put in the name of the database, the version that should be run, how many cores our cluster should have, and which config version we should use, and which secrets we should use. So there are a couple of concepts in here. So first, we're running clusters. We're running clusters because we want to be fault tolerant. If one particular container dies, and this happens quite frequently in a cloud environment, we don't want to face this downtime to our users. So we want a cluster for fault tolerance. On the other side, we want to have a cluster for uptime. So if we want to roll out an update, either a Neo4j update or a configuration update, we don't want to have a downtime for our users. So we can do a rolling upgrade on our data stores when we have a cluster. So my suggestion for you, if you're running a data store, try to make cluster happen. We pass in the configuration and the secrets via the Kubernetes way of doing it. So we're using config maps, and we're using the Kubernetes secrets API to pass in that. And we're just passing in the references because we want to independently update the configurations from this configuration. And we run incremental backups. So most data stores nowadays can run incremental backups. So how that happens is, to go back to our data one example with the $1 million invoice. So the data store will look through the transaction IDs, and when you start an incremental backup, it will compare the last transaction ID of your backup with the transaction IDs in your data store, and it will only back up the delta between the already backup data and the current live data. So for us, it's quite easy and quite fast to do backups quite frequently because the deltas are quite small. So basically, we're running backups constantly. And on the other side, we put the result of the backup to a distributed storage. So we want to make sure that the data of our customers will survive a full outage of the entire data center. So we put it on storage and maybe also replicate to a different availability zone. So, and this is great for us because we're not forced to use remote storage in our production databases. So we can use local SSDs to get the most performance for our users and do the backups, then do the slow work to do the backups and push it to remote storage. And also, if you always have a up-to-date backup, letting a node join to your cluster is also really fast because you can spin up a new instance, give them the last transaction IDs, and then only let the last delta be replicated through your cluster technology. Okay, I think we're good in the time. I would like to thank CBS and the Big Bang Theory crew for this amazing series. I hope you enjoyed these funny pictures as much as I enjoyed this series, and hope you enjoyed the show. So thank you very much. If you have further questions, do we have master of ceremony? Do we have time for questions? Great. So maybe we have time for a question or two.
Hey, we have a microphone. Who wants to ask a question?
Oh. If you don't get your question answered, find me and let's start the discussion. Yeah.
Early on in the slides, you mentioned big beefy servers and remote storage.
Yes.
By pushing the remote storage to a SAN, don't the people implementing the SAN have exactly the same problem that you pushed away?
The problems that I pushed away.
Yeah, the problem of replication, concurrent access.
Yeah, but like if your database have an inbuilt replication, why would you want to do the same on the storage layer? So you would have replication on 2 layers. So the thing is, most modern databases have inbuilt replication. It doesn't matter if it's a SQL store, if it's a key-value store, if it's a document store or graph store. Most of the technologies have inbuilt replication. So the data store would replicate the data on its own. So you don't need to rely on a distributed storage if you have inbuilt replication in your data store. Okay. Thank you very much. So I think, do we have time, or should we move the discussion out of the presentation? We do have time for one question. All right. Thank you very much. Enjoy your conference, and thank you.